Welcome back to our Chem 152 video series. In this video, we'll be working an acid-base titration problem. We begin with a 1 gram sample of KHP dissolved in 50 milliliters of water. KHP is a weak acid, and we're given the Ka and the molar mass. We also say that the KHP is titrated with a solution of 0.200 molar NaOH. First, we'll write the reaction that takes place between the KHP and the NaOH, and then find the Kb of the conjugate base that we make. First, we must realize that KHP is actually potassium bonded to H and P. This potassium is a 1A metal, and so it will break off from the HP, giving us K positive and HP negative. Now, HP is an abbreviation for the phthalate ion. Note that this is not potassium, but the capital P just stands for phthalate. The phthalate ion is an amphiprotic species. It starts with an H and is also negative. However, we're placing that KHP with NaOH. Na is also a 1A metal, giving us Na positive and OH negative. OH negative is the hydroxide ion. The hydroxide ion is always going to be a strong base. For that reason, even though the phthalate ion is amphiprotic and could act as an acid or a base, the fact that we're placing it with a strong base forces the HP negative to act as a weak acid. Let's look at what happens when we place a weak acid with a strong base. The weak acid is HP negative and the strong base is OH negative. If HP acts as an acid, it loses its H and becomes P2 negative. The base picks up an H, and rather than having one H, it now has two, and it makes water. Therefore, our weak conjugate base is P2 negative. We can also find the Kb of this conjugate base by taking K water divided by Ka. We can take K water to be 1 times 10 to the negative 14th. In this class, we'll treat that as a constant, and divide that by the Ka of the acid we started with. The Ka of the acid we started with is 3.9 times 10 to the negative 6th. Then we go to a calculator and divide. We end up with 2.56 times 10 to the negative 9th. This will be our Kb value for P2 negative. Next, we can find the equivalence volume. When they ask you for equivalence volume, what they're really asking is, how much base do we have to add in order to reach the equivalence point of this titration? Let's keep in mind that we have 1 gram of KHP to start with, but we have to go to moles first. In order to reach moles, we'll take that 1 gram of KHP and divide by the molar mass. The molar mass for the KHP is 204.22. We can divide this in a calculator, and we'll get 0.00490 moles. Now for the OH, we know that the amount of OH we've added is the molarity times the volume. And at the equivalence point, we're going to set the moles of acid equal to the moles of base. So we'll say the moles that we just found for the acid must equal the molarity times the volume of the base. The molarity we already know for the base is 0.200 molarity. Therefore, the liters of base that we need is going to be 0.00490 divided by 0.200. We'll end up with 0.0245 liters, or if you prefer, 24.5 milliliters. We find that by shifting the decimal point over by 3 places. Based on this equivalence volume of 24.5 milliliters, we can draw a titration curve. We place pH on the y-axis, and then we'll place our ml of base on the x-axis. When we have 0 milliliters of base, we have just weak acid. Therefore, we would expect our pH to be fairly low. We'll mark that as point A. As we add more base, we would expect our pH to go upward because base increases our pH. We'll draw that on the graph and we'll label that region B. The reason why pH increases is because we are losing HP negative because we're consuming it by using the strong base. And we are making P2 minus. Now you may remember from a previous video, if we have an acid and its conjugate base in the same solution, what we have is a buffer. Therefore, because we have a buffer, we can expect the pH not to increase very much. It will increase, albeit slowly. However, eventually, we'll add so much strong base that we won't have a buffer anymore, and at that point we can expect our pH to spike very high all at once. We'll label that point C, right here in the middle of the jump. This will be our equivalence point. At our equivalence point, we'll have lost all of our HP and we'll have just P2 minus. Once again, that was our conjugate base. Eventually, as we continue adding base after the equivalence point, our pH will level off at a very high level. That's region D, and in region D, we'll have extra strong base. Of course, the strong base that we added was OH minus. A typical titration problem will ask you to find the pH in each of the 4 regions. Point A, which is where we have just weak acid. Point B, which is the buffer region, where we have both weak acid and conjugate base. Point C, at the equivalence point, where we have just conjugate base. And region D, where we have extra strong base. We'll begin with region A. The next part of the question asks us to find the initial pH of the solution, where we have just weak acid. And if you don't know what to do, try reacting the weak acid with water. We'll start with our weak acid, HP negative. Add water. If HP negative is the acid, we're going to lose an H and make P2 negative. If water is the base, it will gain an H and become H3O positive. We'll need to construct a reaction table to figure out what our new H3O is. However, to get this table started, we're going to have to find the molarity of the initial HP negative. The molarity of HP negative is our moles divided by our liters. The moles of HP negative we found in step 2 of our previous problem. Just as a reminder, the moles we found in that part were 0.0049 moles. The liters are effectively given in the problem. Notice that we were given 50 milliliters. If we move the decimal point left 3 times, we'll end up with 0.050 liters. Therefore, we'll divide the moles over the liters. 0.0049 divided by 0.050. We'll end up with 0.098 molarity. We now place that molarity underneath HP in the initial line. We don't start with any P2 negative, and we don't start with any H3O, and we don't need to write anything for water. So the only math we need to do is to find the initial molarity of HP negative. When we react, we know this is going to go down by some amount because we'll use some of it up. and then we'll gain a little bit of P2 negative and a little bit of H3O. It's the H3O that will help us find the pH. So at equilibrium, our HP negative will be 0.098 minus X, our P2 negative will be X, and our H3O positive will also be X. Based on this, we can write a Ka equation for this reaction. We'll have the products divided by the reactants. The products are going to be the P2 negative and the H3O, so we'll have X times X, over the reactants, which are 0.098 minus X. And we'll set this equal to the Ka, which we have in the second line of this problem, 3.9 times 10 to the negative 6th power. We'll bring this equation forward and try to solve it. Ordinarily, we would have a second power quadratic equation that we must solve in order to find X. However, because our K is less than 1 times 10 to the negative 4th power, we can use the small x approximation. The small x approximation states that our X compared to our initial molarity of 0.098 will be very small, and so if you have an added or subtracted X, you can safely ignore it. And this will simplify our equation to x squared over 0.098 equals 3.9 times 10 to the negative 6th. Now we take the denominator and multiply it to the right side and end up with x squared equals 3.9 times 10 to the negative 6th times 0.098. We multiply 3.9 times 10 to the negative 6 times 0.098 in the calculator. We'll end up with x squared equals 3.822 times 10 to the negative 7th power. Then we take the square root on both sides. On the left, we'll end up with x, and on the right, we can go back to the calculator and take the square root. We'll end up with 6.18 times 10 to the negative 4th power. This means that our HP negative will remain at 0.098, our P2 negative will be 6.18 times 10 to the negative 4th, and our H3O will be 6.18 times 10 to the negative 4th. Now remember that our pH can either be negative log of H3O, or it could be pH equals 14 plus log of OH. However, since H3O is what we have, we'll use the first option. So we'll say our pH is equal to negative log of 6.18 times 10 to the negative 4, and once again we can go back to the calculator to find that. We'll end with 3.21 as our initial pH for this titration. We can return to our graph and label this initial pH at this dot labeled A as 3.21. We'll also label this as having added 0 ml of our base. Now we move on to part B and look at what happens in the buffer zone. Our next question says, what is the pH after adding 15 milliliters of the NaOH solution? Let's write our reaction once again. We have some amount of HP negative plus some amount of OH negative combining. HP negative loses an H and becomes P2 negative. OH minus takes an H and becomes water. Initially, we have 1 gram of HP negative. To get the number of moles, we divide by the molar mass. We found the answer to this previously, and it was 0.00490. To find our moles of OH, we will not be using molar mass. Instead, we will be taking molarity times volume. Our volume must be in liters, and we do have the molarity of the OH. That is 0.200. We multiply that times the volume that we were given in the question. This time we know that we're adding 15 milliliters, and that will be 0.015 liters if we move the decimal point to the left by 3 positions. If we multiply these together, we end up with 0.003 moles. We place that underneath the OH negative. We start with no P2 negative, and then our water we don't have to write. Now we'll complete our ice chart, and now we have to remember that if we have a strong base, this reaction will go to completion. This means we will run out of whichever of these two reactants is lower in moles. We can see that 0.003 is definitely less than 0.0049, therefore we will lose all of our OH negative, and we will lose an equal amount of our acid, HP negative, and we will gain the same amount of P2 negative, our conjugate base. Now, if we take our initial and subtract the change for the HP negative, we will have 0.00190. For the OH negative, we'll have none left. And for our P2 negative, we will have 0.003 moles. Therefore, we have a weak acid still remaining. We have no strong base. And we have P2 negative, which is our weak conjugate base. Since we have some weak acid and some weak base, we still have a buffer, and therefore we can go to our buffer equation to find the pH. Now recall that our buffer equation says that pH is equal to negative log of the Ka plus log of the base divided by the acid. We have the Ka because that was given to us in the problem. It is 3.9 E negative 6. We'll place that in the Ka position. Then we'll add plus log of the base over the acid. Let's remind ourselves that the base here is P2 negative. And the acid is 0.00190 for HP negative. Therefore, we'll have 0.003 on top and 0.0019 on the bottom. And then we can enter all of this into the calculator at once. So we'll end up with a pH of 5.61. We can go back and label this amount on our titration curve. Keeping in mind that point C is going to be at 24.5 milliliters, we have a pH at 15 milliliters, which will be approximately at this mark, where we got 5.61. We can use this technique and this equation to find the pH anywhere inside of region B, that buffer zone between point A and point C. Now let's try to find the pH at point C at the equivalence point. Before we start the math, let's do a little bit of setup. We began with 1 gram of HP negative in 50 milliliters of water. We found previously that was 0.0049 moles. Then we added some amount of OH, but we found the amount of OH that we needed to reach the equivalence point was 24.5 milliliters. And that the molarity of NaOH given in the question is 0.200. Now at the equivalence point, we know that the moles of OH must be the same. 0.0049 moles. It's important to realize that at the equivalence point, all of the moles of HP get used, and all of the moles of OH minus gets used. Therefore, we will make that same number of moles of P2 negative. Therefore, we have no weak acid remaining. We also have no strong base remaining. In fact, we have only weak conjugate base remaining. Some people may be tempted to go straight to the buffer equation here, but we actually can no longer use the buffer equation because we have only weak conjugate base and no acid to go with it. The only thing left to do then is to take that weak conjugate base, react it with water, and see what happens. Before we go on, let's make a note that we have added 50 milliliters plus 24.5 milliliters in order to complete our titration, in order to reach this equivalence point. We'll also need to make note of the final volume before we continue. We had 50 milliliters of acid and 24.5 milliliters of base. If we add those together, we will get 74.5 milliliters of solution. With our knowledge of the number of moles and the number of milliliters, we can create a reaction table to figure out what happens with the P2- and what the pH is. Let's begin by writing P2- plus water. Let's figure out what this does before we go any further. We know P2- cannot be an acid, it must be a base, and if it acts as a base, it will give us HP- because it'll gain an H. That H has to come from water, so you'll lose an H from water and make OH negative. Now, to construct this reaction table, we'll need to find the molarity of P2-. To find molarity, we take the moles divided by the liters. We have 0.00490 moles, and for our liters, we'll take the decimal point in this 74.5 and move it over by 3 positions, giving us 0.0745. When we divide, we will get 0.0658 molarity. We'll write that in the initial line underneath P2-. We don't have to write anything for water, and we don't have to write anything other than 0 for HP- and OH-. We know that we're going to lose a little bit of P2-, but not very much, and we'll gain some of HP- and OH-. Therefore, we can write that our P2- is now 0.0658, and our HP- and OH- are both X. In order to set up the equilibrium equation, we'll also need to find the K value. Since this is a base, we will be finding a Kb value. Now, Kb is going to equal K water divided by Ka. However, we calculated this all the way back in step 1 because our K water was 1 times 10 to the negative 14th, and our Ka was 3.9 times 10 to the negative 6th, and when we divided, we got 2.56 times 10 to the negative 9th power. Now, based on this, we can write an equation for the Kb. When we write our K equation, we'll say Kb is equal to products over reactants. Our Kb is 2.56 times 10 to the negative 9th. Our products are both X and X. When we multiply, we'll get X squared. The reactants are only 0.0568. Our reactants are just P2- and we'll have 0.0658 minus X. We don't have to write anything for water. However, because our K is very small, it is definitely less than 1 times 10 to the negative 4th, we can use the small x approximation. This means that this minus x attached to the 0.0658 is very, very tiny, and we can safely ignore it. Therefore, our equation will look like 2.56 times 10 to the negative 9th equals x squared over 0.0658. We can multiply this 0.0658 to the left side, and then take the square root of both sides. And we'll end up with 2.56 times 10 to the negative 9th times 0.0658 equals x. We can put this into a calculator. we'll get x equals 1.3 times 10 to the negative fifth power. Note that this x is equal to our OH. So after all of this setup, we can finally find the pH. Our pH can either be negative log of H3O or equal to 14 plus log of OH. Since OH is a member of our equation, we'll use the second form of the equation to get our pH. We'll have pH is equal to 14 plus log of 1.3 times 10 to the negative fifth power. We'll end up with a pH of 9.11 after we input this in a calculator. With that completed, we'll go back to our pH chart once more and add that to our picture. So at this equivalence point C, we have a pH of 9.11. Now that we've worked with cases A, B, and C, let's finally move on to case D, where we've added extra strong base past the equivalence point. For the final part of this question, we now have 30 milliliters of NaOH that we're adding to our acid solution. Before you do anything else, let's find moles. For our HP negative, we had 1 gram divided by 204.22. So as before, we start with 0.00490 moles. But we have a different number of moles of OH now. We're taking the molarity times the liters. Our molarity was 0.200, and our liters are now 30 milliliters or 0.03 liters. When we multiply, we'll get 0.006 moles. We start with no P2 minus, and we don't have to worry about water. Now we check which number of moles is lower. The lower number of moles this time will be our HP negative. We will lose all of it. And we will lose the same number of moles from both reactants. We will gain that number of moles for our product. When we do the subtractions, we will have no moles of weak acid left. We'll end up with 0.0011 moles of our strong base. And we'll end up with 0.00490 moles of our weak base. So notice that we have a solution that is both strong base and weak base, but has no weak acid left. We certainly don't have a buffer here because we would have to have some weak acid in order to be a buffer. In fact, what happens in this case is that you'll have strong base, and that's much stronger than your weak base, and so the strong base will control the pH. Because the strong base controls the pH, we only need to use our strong base to find the pH. That is, if you have a mixture of strong and weak, the strong has much more control over the pH than the weak base does. Therefore, we can ignore the weak base and look only at the strong base. In order to find the pH, we'll first find the molarity of the strong base. The molarity of the strong base is equal to our moles divided by our liters. We already know the moles are 0.0011 moles. In order to get the liters, we can look at the question's volumes, and we'll notice that we started with 50 milliliters of water and added an additional 30 milliliters of NaOH. If we take 50 plus 30 milliliters, we'll have 80 milliliters. But we must write this in terms of liters, not milliliters, and we'll have 0.080 liters. We'll take our moles divided by those liters and put that in a calculator. When we do so, we'll end up with 0.01375 molarity. Now that we have the molarity, we can find the pH. Our pH will either equal negative log of H3O or will equal 14 plus log of OH. However, since we had a strong base, it makes more sense to use the second option. Our pH will equal 14 plus the log of 0.01375, and we can place this in a calculator as well. We will end with a pH of 12.14. We'll go back to our graph one more time. On our graph, we'll label that 30 milliliters we just found. We'll mark that on the graph, and we'll say 12.14 is our pH at that position. So now we've found the pH at 4 points along the graph: at the initial point, in the buffer region, at the equivalence point, and after the equivalence point as well. Thank you for watching, and we'll see you again soon.